Good evening, Dr. Taimur. Taimur.
Hi, sir. Good evening.
Yeah, good evening. Good evening.
Yes, sir. Sir, I am making a call to SPARC coordinator.
Anyway, you start.
Okay, sir. Okay, sir.
Good evening. Good evening.
Good evening.
Good evening, sir.
Good evening.
Dr. Taimur.
Okay, sir. Have you joined? Good evening.
Yes. I'm in the line.
Thank you, sir. Thank you. Before starting the inaugural session, I request to all of you, please mute your microphone. Okay. Good evening, good morning, and good afternoon to one and all. The ongoing global pandemic situation due to COVID-19 has unluckily disturbed exchange of information among the scientific community through the conventional in-person gathering in different workshops, conferences, etc. Hence, we believe that the learning and knowledge exchange, even in this ongoing tough time, should not stop. In the meanwhile, the virtual mode of communication has come up as a productive alternative and made it easier for all of us to connect globally. In this spirit, National Institute of Technology Silchar, in association with Delhi Technological University Delhi and Queen's University Kingston, Canada, has desired to bring and connect the scientific community through this one-week-long virtual event. So, with an immense pleasure and gratitude, I, Dr. Taimur Khan, convener of this virtual event, on the behalf of organizing committee, welcome you all to this one-week-long Indo-Canada SPARC Student Research Conclave on RF Energy Harvesting Systems, SRC-2020, hosted by Electronics and Communication Engineering Department, NIT Silchar. SRC-2020 is a week-long student research conclave on radio frequency energy harvesting systems. Energy harvesting, also known as power harvesting or energy scavenging or ambient power, is the process by which energy is derived from external sources with solar energy, thermal energy, wind energy, kinetic energy, wireless or RF energy, captured and stored for small wireless autonomous devices like those used in wearable electronics and wireless sensor networks. The RFEH process involves harvesting electrical energy from RF signals. The targeted power is usually derived from ambient RF energy sources such as GSM cell towers, base stations, wireless local area network routers, Wi-Fi hotspot, TV, radio broadcasting, and some unknown RF transmitters. RF energy harvesting systems can be built cheaply in small dimensions. RFEH suits many applications such as a smart house, a smart grid, healthcare, Internet of Things, and wireless body area networks. The aim of this SRC 2020 is to provide a common platform to the student researchers working in the emerging area of RF energy harvesting and allied domains for delivering talks in their specialized research topics. The course structure of this research conclave is designed in such a way that the students, research scholars, faculty members, and industrial professionals will get an exposure to familiarize themselves towards the recent pertaining to radio frequency energy harvesting systems. This student research conclave is fully sponsored by Ministry of Education, formerly known as Ministry of Human Resource Development, Government of India, under the SPARC scheme for promotion of academic and research collaboration as an academic deliverable of the ongoing SPARC project. The SPARC aims at improving the research ecosystem of India's higher educational institutions by facilitating academic and research collaboration between Indian institutions and the best institutions in the world from 28 selected nations. The major outcome of the SPARC initiative is to make a strong research collaboration between Indian research groups with best-in-class faculty and renowned research group in the leading universities of the world in areas that are at the cutting edge of science or with the direct social relevance to the mankind, especially of India. Now, on the behalf of organizing committee, I would take this opportunity to welcome our respected director, Professor Shivaji Bandyopadhyay, Dean Research and Consultancy, Professor M. Ali Ahmed, Institute SPARC Coordinator, Professor Upendra Kumar, Chairperson of this virtual event, Professor K.L. Vaishnav, and all other invited guests who have graciously agreed to attend this inaugural session. Next, my warm welcome to the SPARC team, Professor Yahya Antar, Foreign PI from Queen's University, Canada, Professor Frondorfer, Foreign Co-PI from Queen's University, Canada, Professor Ashok Day, Indian Co-PI from Delhi Technological University, Delhi, India, and last, myself, Dr. Taimur Khan, as an Indian PI from NIT Silchar, who have kindly agreed to organize this student research conclave. My sincere gratitude to all the invited student speakers, both from India as well as from foreign. Mr. Sam Gosen, PhD scholar from Izmir Kalebi University, Turkey. Mr. Kasan Dotov, PhD scholar from Nazarbayev University, Kazakhstan. Ms. Neeta Singh, JRF from Jawaharlal Nehru University, Delhi, India. Mr. Vikrant Kain, PhD scholar from Jawaharlal Nehru University, Delhi, India. Ms. Slebi Divakaran, PhD scholar registered in APJ Abdul Kalam Technical University, India, as well as our internal PhD students, including Ms. Dibanjali Sarkar, Ausar Partim, Muhammad Ahmad, Muhammad Ehsan Halimi, Dasri Surendra, Ashutosh Srivastava, and Partha Pritam Shom, who has been recently awarded his PhD from NIT Silchar in just 2 months back. I also welcome members of the organizing committee of SRC 2020, Dr. Naresh Babu, faculty from CSC department, and our PhD scholars, Mr. Dasri Surendra and Mr. Suman Modar, and appreciate them for their willingness and command in managing different activities associated to this virtual platform on which we all are connected this evening and will continue so far for the next 5 days. In last but not least, I extend my warmest welcome to all the participants belonging to different parts of the globe, irrespective of their different time zones, and who have registered for this webinar event, and hope that the 5 days of a webinar event will be beneficial to all of you. Next, in the continuation of further proceeding, first of all, I would take the privilege to call upon the chairperson of SRC 2020, Professor K.L. Vaishnav, to give the welcome address to the participants. Professor K.L. Vaishnav. Professor K.L. Vaishnav. Okay. Next, I would now request Institute Coordinator SPARC, Professor Upendra Kumar, to speak a few words on this event, SRC 2020.
Very good morning and very good evening to all of you. Honorable Director Professor Shivaji Bandyopadhyay, Dean Research and Consultancy Professor M.A. Ahmed, Head of the Department Dr. K.L. Vaishnav, all the expert speakers, faculty members and participants. It is my great pleasure and honor to welcome you all in this inaugural ceremony of the Indo-SPARC course. This course is the part of SPARC project of Dr. T. Khan and Professor Ashok Day, which is in collaboration with the international PI, Professor Yahya and Professor Fundus of Queen's University, Canada.
Yeah. Hello. Taimur.
Sir.
Yeah. Should I continue or?
Sir, after Upendra, sir, I will call you.
Okay. Thank you. Please.
Sir, carry on.
So, yeah. So sorry for the interference. So this is the part of the SPARC program, and Dr. T. Khan has already told you about the SPARC program and what is SPARC. Currently, we are having 4 such projects at NIT Silchar, we have also applied for 14 number of new SPARC projects for the year 2020-21, and we are hoping for a good number of projects. I would like to thank all of you for participating in the program. Special thanks to all the expert speakers for giving their valuable time for the course. Thanks to SPARC MHRD. We are also grateful to our director sir for his support and encouragement. I also thank to our young faculty coordinator, Dr. T. Khan, and his team for organizing this program. Thank you all. Have a nice day. Over to Khan.
Thank you very much, sir. Thank you. Now, I would like to call upon Chairperson of SRC, Professor K.L. Vaishnav, to speak a few words on the event.
Yeah, again, sorry for the technical glitches. So very good that afternoon, evening, and morning to all. With our Honorable Director, Sir, Professor Shivaji Bandyopadhyay, the Chief Patron of this workshop, then Professor Upendra Kumar, the Patron of this workshop, already spoken, then our Dean of Research and Consultancy, Professor Muqaddas Ali Ahmed, then for the SPARC team, my heartiest congratulations to and welcome to Professor Y.M.M. Antar from Queen University, Professor Ashok Dev from Delhi Technical University, Delhi, Professor A.I.M. Frundufar from Queen University, Canada, other distinguished invited speakers, my dear colleagues, my dear friends, and other delegates. We are very much happy the way this SPARC really inviting many scholars, many resource persons, and taking our visibility beyond the horizon. We can see that number of countries joined. The time was there, we are known within the country. This program really has given the touch. You can see the many participants from Kazakhstan and other countries. Thankful to the entire team of this park for such good initiative. Despite we are different countries, but this program has really made us to so close, removing all those barriers of distance. I appreciate entire team. I appreciate the authority of NIT Silchar for encouraging faculties, as already Professor Upendra Kumar already said, that there are a number of more SPARC, I think, projects they have been submitted to the ministry. We're expecting that a few more will come, and that's really will bring a really wonderful environment or conducive environment to work together across the globes. With this, I again thanks to Dr. Taimur Khan, Professor Ashok Dev, Professor Y.M. Antar, because this is the third program really I am sitting with them, and I can see the different participants and experts and delegates from the different countries. I am very much happy with this. So I wish that the participants should capitalize the opportunities, because those PhD scholars, those are delivering the speak, really they are working on this area. their expertise on this area. I hope they can give a more light, they can motivate more scholars, young generation to work together, because this RF harvesting is such a thing, is a multidisciplinary and is an emerging area. And really we can fulfill the need of the society. I already said that it is mechanical, electrical, electronics, computer science, everybody need. So hope so this workshops or this conference will give another window through which we can work together. With this, thank you all. Thank you. Over to Dr. Taimur, please.
Thank you, Professor Vaishnav. Now, before calling to Dean RNC, I would like to call upon first Professor Ashok Dey, former Director NIT Patna, to share a few words on the behalf of SPARC team, as Professor Antar is already occupied some other meetings and he has dropped a message to me that I will be joining late. In this way, I would like to call upon Professor Ashok Dey to say a few words on the behalf of organizing committee.
Thank you, Dr. Khan. Director NIT Silchar, senior professors, deans of NIT Silchar, all the international guests, all the students, participants from different countries and from NIT Silchar. I welcome all of you in our this SRC-2020 program. Our main objective to organize this program under this SPARC Indo-Canadian program is to give the all the students who are working on the RF harvesting can get a platform where they will exchange their ideas so that they can enrich in their thinking and in their research program. So I hope that all the PhD students who are delivering lectures in this 7 days program, through this other students who will be highly benefited, and if all of you are benefited through our this SRC 2020, then only we will feel that we are successful to organize this program. With these few words, I again welcome all of you and my best wishes to all the research scholars who are participating in this program, and hope for their bright future. Thank you.
Thank you. Thank you, sir. Thank you very much. Now, finally, I would like to call upon Dean Research and Consultancy, Professor Muqaddas Ali Ahmad, to share a few words on his personal behalf as well as on the behalf of Director Sir, because Director Sir is already attending some other meeting.
Okay. Am I audible?
Yes, sir. Yes, sir. You are audible.
Okay. Good evening to all the members present in this virtual meeting, and good morning to the international members. Respected Director NIT Silchar, Professor Upendra Kumar, the SPARC Coordinator, Professor K.L. Vaishnav, the Chairman and Head of the Department, Professor Ashok Dey from DTU Delhi, Professor M.M. Yahya from Queen's University, Canada, Dr. Khan, who is also one of the Indian PI of the project, all the participants, all the speakers. So very welcome. On behalf of the Institute, NIT Silchar, I welcome all of you to this 1 week student research conclave. The name itself is something special, research conclave. It's neither a workshop, neither a conference, but it is something mixed with a workshop and conference. So it will be very nice platform. I hope this is one of the best platform. And I have seen that there are student speakers, JRF, SRF from various universities, including United Silchar. So this is one of the best platform for all the participants to listen to their peer colleague and the research area. They will have also the opportunity to focus their research area in front of the globe. So as you know, in NIT Silchar also we are organizing student research conclave annually, but that is a bit different, but this is a bit mixed. So again, I would like to congratulate the total SPARC team, particularly Dr. Khan and Ashok Dey and Professor Antar from Queen's University and another co-PI from Queen's University, because this is the third program under this project. So the organizing committee of this SPARC project is doing very excellent job. I would like to congratulate all of you. And please keep doing all those things. And I would like to say to the international and national participants that the NIT Silchar focuses on translational research. That is, we no longer depend on only the research related to paper publication and thesis writing, but the research should be oriented to solve the real problem of the society. Our research should be able to help our society. And that is nothing but the translational research. That is, whatever we are doing, that should be translated to the field problem. We should not be a job seeker. The second objective that we want to follow is that we are not a job seeker, but we want to be a job creator. And that is, we have that innovation center, then SPARC startup center, etc. Through this, we are also focusing the student to go for the innovation. So I will request all the participants to do research that is related to the field problem. And this energy harvesting is one of such interdisciplinary research. Everybody can contribute a lot to solve the problem of the society. So this again, I would like to congratulate all the participants, particularly the student speakers. You will enjoy this. I hope you will enjoy this workshop and this student research conclave. And from my personal behalf, I wish a very successful program. Thank you very much. Over to Dr. Khan.
Thank you, sir, for your kind and motivational address. Now, finally, thank you all for joining this evening for an inaugural session. With this, I conclude this inaugural session. Now, in the continuation, I would like to introduce the very first speaker of the event, Ms. Neeta Singh, who is working as a junior research fellow in Jawaharlal Nehru University, Delhi. Neeta Singh is Ms. Neeta Singh, are you there?
Yes, sir. Yes, I'm there.
Okay. Thank you. Neeta Singh received the BTech degree in Electronics and Communication Engineering and MTech degree in RF and Microwave Engineering from Guru Gobind Singh Indraprasth University, Delhi, India in 2012 and 2015 respectively. Recently, she received the PhD degree from the Faculty of Engineering and Technology, Jamia Millia Islamia, New Delhi, and presently she is working as a JRF in School of Computational and Integrative Science, Jawaharlal Nehru University, Delhi, India. Her research interest includes RF energy harvesting, antenna rectifier circuits, and wireless power transmission systems. With this, I invite Ms. Neeta Singh and welcome her also for this first session and invite her to start the talk.
Thank you so much, sir, for inviting me. Can I present, sir? Hello? Hello.
Just 4 seconds. Just for a second. We are
Okay.
stopping our presentation.
Okay, sir.
Okay.
Now can I present, sir?
Now, yes. Now you can share your PPTs.
So is it visible?
Yes, now it is visible. Yes. Make it full screen.
Yes, sir.
Okay.
Yes, sir.
And on bottom side, there is one icon. You please hide that icon. On bottom center, there is one icon. You hide that icon.
So now it's okay?
Yes, yes. Go ahead.
Good evening, good morning, and good afternoon to all. First of all, I would like to thank Dr. Taimur sir and the organizing team to give me an opportunity to speak on that platform, and it is a matter of honor for me. So, my today's topic for this webinar is Biofree World, the emerging technologies of RF energy harvesting systems. These are my topics I'm gonna cover in this talk. First of all, I will discuss what is wireless power transmission and what's the history behind this wireless power transmission. And after that, I will introduce you what are the energy harvesting, what is the energy harvesting, and what other energy sources are available. And then I will discuss what is RF energy harvesting and how it is beneficial as compared to the other energy harvesting techniques. Then I'll describe the block diagram of RF energy harvesting system. And then I'm gonna discuss some papers of my PhD that shows the design and analysis of Rectina. And then I'll show you the applications of the RF energy harvesting system. So first, before I start the history of WPT, I would like to talk something about the WPT, like wireless power transmission. Why we are moving towards the wireless power transmission? As we all know, we can't even think our lives without electricity in this growing world. To charge or provide power supply, we need batteries or some power source. And wireless power system provides various advantages over other wired power systems, like need of batteries eliminated, no wires required, no e-waste, less environment pollution for as if we use the wireless power transmission, as well as it is environment friendly. It is fast, like we need not to sit near to the power supply cords. We can charge our laptops or e-vehicles even while moving. Or it is flexible as well because it can work even in the harsh environment, and there is no wire installation because maintenance cost is very less. Hence, as we moving towards the history of wireless power transmission, it tells us from where the idea of wireless power transmission system evolved. The very first scientist, like James Clerk Maxwell, he gave the theoretical existence of EM waves, and his work further carried by the Heinrich Hertz, and he designed the first loop antenna that can transmit or receive the EM signals. The concept of transmission of power without wires was first given by Nikola. He demonstrated his experiment in 1899 on this star, as you can see in the figure. This star, and this star is 187 feet tall, called as Wardenclyffe star. And after the experiment performed, it is also called as the Nikola star. Tesla designed a large coil of 16-meter diameter that resonates at a frequency of 150 kilohertz, and he was capable to transmit from 40-kilometer distance and light up 200 bulbs simultaneously. And then the further experiments carried out in this way in different years. Like in 1963, W.C. Brown came with the concept of rectina and able to achieve 50% of conversion efficiency, and but due to the less conversion efficiency further carried his experiment in 1964, and by using point contact diode he was able to achieve 270 watts of power, and because of that he can able to flew the retina helicopter for continuously 10 hours. And recently, in 2006, MIT gave the concept of wireless electricity. They carried the wireless electricity experiment, and they used resonant coupling. But due to this resonant coupling method, the distance is very limited. Um, then we move towards the wireless power transmission. As the name suggests, wireless power transmission is a transmission of power through airs without using wires or cables. This is the trending technology because we are using of wires. We can use it where using of wires are hazardous to human health and environment. It is further divided into the two parts, that is the near field region and the far field region. Near field region has limited space around the transmitting and receiving device. In this method, the time varying field generates the time varying magnetic field. Basically, it also further divided into the magnetic resonance and inductive coupling. It also has the third part, that is capacitive coupling, and all the three parts depends upon the magnetic and electric fields only. And second one is the far field radiation, which shows the RF energy harvesting. It also has the laser power transmission also, but we limit our research towards RF energy harvesting. So I'll discuss RF energy harvesting only later on. I'll start with the near field region. It has, in this slide, you can see we have two types like inductive coupling and capacitive coupling. Power transfer through magnetic field is called inductive coupling, and the power transfer through electric field is called capacitive coupling. As you can see in this figure, the two coils are used. This one is the primary coil, the first one is the primary coil, and second one is the secondary coil. As the primary coil develops an oscillating electric field and generates the time varying magnetic field, the secondary coil detects that magnetic field, and this is responsible for the current flow into the circuit. In the capacitive coupling, we have two configuration, bipolar coupling and the unipolar coupling. In bipolar coupling, we have two electrodes, pair of electrodes, and this electrode replaces the coil. As you can see, in the previous one we use coils, but in this we use electrodes, metal plates, which works as a capacitor here, and it is also called as transverse method. This is called the longitudinal method, and it includes only one electrodes, and power is transferred from transmitter to the receiver. This is the magnetic resonant coupling technique. In this, it is similar to inductive coupling, but only capacitors are included at the receiver and at same as the receiver as well as the transmitter, and it has four configuration: single input, single output, in single input and single output, only one transmitter and one receiver are there. But in multiple input and single output, we have many number of transmitter but single number of receiver. In this configuration, Only one transmitter is there, and different many number of receivers are present. And this is the multi-input and multi-output, that is MIMO. Here the number of various number of transmitter and various number of receivers are present. So these are the different techniques which we use for the near field power transmission. Now we are moving towards the far field region. In far field region, you can see these are the advantages, like it is very reliable, it is very efficient, environment friendly, as we know it will not harm as if we use the wired system, so it is very harmful. It is very fast, we need not to sit to the power supply cords. It is very fast, low maintenance cost. Maintenance is not required because the power is transmitting through wireless, and it is also flexible. So it contains two or three subparts also, like RF energy harvesting and the optical transmission, also called the laser transmission. I'm gonna discuss about introduction to energy harvesting. Energy harvesting is the process of capturing ambient energy and storing its electricity after conversion. This allows us for remote charging applications. And if we cannot capture these freely available energy, it is lost in the form of heat, light, sound, or vibration, maybe. But now the question arises, why we all talk about wireless systems only? Why we are talking about wireless communication, wireless power transmission? What's the problem with the wires? There are main three reasons why we not shows important towards the wire technology. First of all is electric shocks are caused due to the broken wires or the cable faults. And in an explosive environment, the wire can work as a source of ignition. And when it also harmful to the birds. They also come contact of shocks. And second one is through wired power transmission, there is a problem of power loss. Like in India, around 20 to 30% of power is lost due to wired electrical systems. As the technology enhancing, more and more electronic devices are being used. But the batteries and wires are used have limited lifeline, and their decomposition creates environment pollution, also called as e-waste. The decomposition of batteries and wires, as you can see in this figure, the decomposition of batteries and wires releases large amount of toxic chemicals, and these harmful chemicals can directly affect our body through air. Like some of the chemicals you can see here, like lead, it damages the brain, also can cause coma when body directly comes in contact with it. The mercury, it acts as a poison for kidney, eyes, skin, and damages the central nervous system. Arsenic, it increases the risk of cancer in lungs, kidney, and liver as well. And copper, it damages the kidney. Bromine affects the heart. And PCB is polychlorinate biphenyl, and this chemical damages the immune system, and it also affects the reproductive system of the body. And the cadmium, it weakens the bones for the lifetime. So the decomposition of batteries and wires is still a problem, and it is the global problem because it is directly affecting to our body. As we see, there are various energy sources available in the environment. Like huge amount of energy came to us from sun, so we can harvest the energy from sun as well. And then wind turbines are there. It used to harvest the wind energy. Then we have thermal energy also, which is harvested by means of temperature difference method, which produces the voltage difference. We have vibrational source also, we have RF energy sources also, but RF energy can harvest from the source of RF signals present in the environment, and it shows various advantages over these other energy sources, because these depends upon the climatic conditions and available all the RF energy available all the time, like it is available in the daytime as well as in the night also. So, this is more beneficial as compared to the solar, the other sources. But some energies like sunlight, nuclear energy, wind energy, they give us good amount of power conversion. Like we can harvest and harvest these, and if we harvest these energies, we are able to get good amount of power. But if we limit our harvesting to RF energy sources, vibrational sources, or acoustic energies, we limit our output towards the milliwatts only. Now this is the block diagram. This is the freely available energy which is present in the environment, and it can be any source like Wi-Fi routers or TV towers which is present in the which is present, and laptops, your mobile phones, through which the EM waves radiated in the environment. And this is the antenna. This is the receiving antenna generally, because it receives the signal that is freely available in the environment. And this antenna resonates at if the antenna resonating at the 2.45 gigahertz, suppose, then it can receive the signal only which is freely available at 2.45 only. Like Wi-Fi router, it works at 2.45. So this antenna receives the signal at from this router only. So this antenna works for that particular frequency. After that, and it can be of any type of antenna. And then after we have rectifier. As you can see, this is the block of rectifier. It consists of diodes, and generally here we use Schottky diode, because Schottky diode shows various advantages over other diode. It is unipolar device, and due to the absence of current flow from metal to this, it is high speed switching device also, or its voltage drop is very less, that is 0.15 to 0.45 volt. Hence, Schottky diode is very much in use at microwave frequencies for rectification. This is the matching network which is used between the antenna, the receiving antenna, and the rectifier. This matching network provides the matching impedance. It matches the impedance of the antenna and the rectifier, so that maximum power is transferred to the rectifier. And this is the DC pass filter, because the it is used here because after the rectification, the output DC voltage is not pure. It still consists some ripples. Hence, to remove those ripples or suppress those ripples, the DC pass filter is used. And after that, the pure DC is achieved at the output, and this can be directly used, or we can store at the storage device and use for the later use. We can use it later. Then I have RF energy harvesting system. In RF energy harvesting RF energy harvesting system shows various advantages as other, like it is available on demand, works in perpetual dark locations also, works in hazardous locations also, provides mobility, can store energy for later use, as I discussed in the previous slide, can be embedded between walls and device, that is used to complete this process is called rectina. The rectina, the whole device that covering this whole process is called rectina, also called as the rectifying antenna, because rectifying suggests the rectifier and antenna is the receiving antenna. So its name is rectina. These are the available energy sources that you can see here. There are generally two types of energy sources, ambient energy sources or the dedicated energy sources. The ambient energy sources are those which is you can see in the table. These are the ambient energy sources and are present, it is present in our surroundings freely. As we know, number of mobile subscriber increases day by day, but these sources provides less amount of power to charge the batteries, like sometimes cell phones, radio towers, Wi-Fi routers, laptops, TV signals. This provides this amount of available power in the environment. But generally, we are working on 2.45, like we are working on ISM band. So the available energy is very less, and to increase this energy, we move towards the dedicated energy sources. These energy sources are on demand supply and use license-free band to design the source. Like it is directive towards the receiver, which increases the conversion efficiency also. If like we can design the transmitting antenna also that can transmit at the same frequency as the receiving antenna. Now this is now we'll start with the receiving antenna. Antenna is the basic part of the retina which receives the EM signals, and that is freely available from different energy sources, as we already discussed. So some of the properties we need to follow when we design the receiving antenna. That first of all is the gain should be very high, means the antenna, the receiving antenna should be very directive, and also the miniaturization of the antenna is also needed, because if we need to integrate our antenna on some device, then its size should be very small. And nowadays the researchers are working on multi-band and the broadband antennas, because to harvest the single band antenna, the conversion efficiency is very less. And if we are able to harvest the energy from different sources like Wi-Fi routers or TV towers, and simultaneously these different frequencies. So the more amount of power can energy can be received by the antenna. Hence, we can get more output at the receiver, as well as, and two more important properties, that is harmonic suppression property as well as circular polarization. Harmonic suppression property is needed because harmonic suppression property affects the performance of the retina. It back radiates towards the antenna and interference causes, which reduces the conversion efficiency. Circular polarization is also needed for wireless power transmission, because if the system is not circularly polarized, polarization mismatch is there, and it again decreases the efficiency of the system. So first of all, we talk about the harmonic rejection antenna, how we gonna achieve this harmonic rejection antennas. So the diode in the rectifying circuit generates higher order harmonics, which reduces the conversion efficiency of the antenna. Therefore, a low pass or the band pass filter is integrated into the rectifying circuit. Now, these filters are omitted from the designing of the retina, because if we use the antenna itself having the harmonic rejection antenna, or itself having the low pass filter or the band pass filter, it removes the higher order harmonics, and hence the need of filter after antenna and before rectifier is omitted. Also, it reduces the size of the device. So there are two methods to achieve this. That first of all, DGS, that is defected ground structure, and then with the help of slot or slit, we can achieve harmonic rejection antennas. DGS is a lump circuit which is working as a filter, and it passes only the resonant frequencies and rejects higher order harmonics. The capacitance and inductance of the transmission line vary with the shape of DGS. Like if here you can see the different shapes of the DGS. Through this we can achieve different filters, and this filter only passes the resonant frequency and suppresses or rejects the higher frequencies. As well as this slit and slot, the current around the around the slot prevents the formation of undesired harmonics. The loaded slot or slits changes the flow of current on the patch, hence controlling the harmonics. This slot size and shape can be calculated according to the desired frequencies. Like what frequency we need to suppress, we can design this slot. We can cut the slot accordingly. Yeah, different types of slot, different shapes of the slots are there, like right angle triangle, rectangular, elliptical, rhombic, square ring, triangular, hexagonal, circular ring, pentagonal, and other shapes also. We have cross slot, U-shaped slot, T-shaped slots, and many more slots are there to achieve the higher order, to remove the higher order harmonics. Then we have circular polarization. In this polarization, both electric field coordinates are propagating in the direction of plane of same direction of plane of polarization, and all are perpendicular to each other. For wireless power technology, circular polarization is preferable due to low polarization losses. If the transmitter, like if we have the transmitter and receiver, both are linearly polarized, then after reflection, incident wave changes its direction, and the receiver not able to receive the signals properly. Hence, the conversion efficiency, or the signal received less, and conversion efficiency also decreases. There are some different methods to achieve this circular polarization, like cross slot, unequal cross slot arms we can use to achieve the circular polarization. Truncated corners are very much in use. Generally, we can use this truncated corners to achieve the circular polarization. Tuning stubs are also very much in use to achieve the circular polarization. Then we have the matching network. The impedance matching circuit is a network that matches the impedance of the source and load. Like you can see in this figure, we use the matching circuit network in between the input and the load. And this process is also called as tuning. With the help of maximum power transfer theorem, the maximum power can be transferred from the source to the load. These are some factors we need to keep in mind when we gonna design matching network. First is bandwidth. It is very simple or easy to match the single frequency, but when we are designing for the multi-band or the broadband, it is very difficult to match at all the frequencies or for the wideband frequencies. So we need to consider this also while we design the system. Then we have the complexity. Complex network offers very it is not very reliable, and it is size can also increases. So the matching network should not be very complex, and it should be adjustable. Adjustable means the load used, the resistance used at the load, that is the load resistance. If its value changes, then it will not affect the conversion efficiency. Matching network should be flexible, and it can It can matches the variable load also. Implementation means for different applications, different matching networks are available, and we need to design for that particular application the perfect matching network. These are the topologies of matching network: the lumped elements, the tuning stub, and the quarter wave transformer. Lumped element, we have L network, three element network. L network is the very simplest network system, and in three element networks, it consists of two networks, that is pi network and the T match network. In pi network, the L is connected in series. Two L networks are connected in series, and in the pi network, and in the T network, the two L are connected in shunt. Then we have the tuning stubs, the single stub and the double stub. These stubs are as a distributed matching circuits, and these are perfect matching networks because they provide us the maximum perfectly matching circuits. And then we have the quarter wave transformer. Quarter wave transformer is used where real load is there. If we have the complex load, then quarter wave transformer is not reliable. Then we need to shift towards these two matching network topologies. Quarter wave transformer is a simple network which is connected between the source and the load, and the that network is λ/4. That is why it is also called as quarter wave transformer. Then theory of rectifiers. Rectifiers are the building block of the wireless energy harvesting system. A rectifier converts the captured ambient energy from the environment into the DC part. And this is the basic block diagram of the rectifier. The diode is there, which is used between the series resistance and the load resistance. And this is the capacitor which stores the energy. And also it works as a filter here, as we already talked about the DC pass filter. So it is working filter as a filter here, and removes the ripples also. These are different rectifier topologies. This is voltage doubler, Greneker circuit, voltage multiplier circuit, and Willard circuit. In voltage doubler, you can see the D2 and C2 works for the positive half cycle, and D1 and C1 works for the negative half cycle. D2 works for the positive half cycle because it is forward bias. It works for the forward bias, and when it is reverse bias, then D1 is on, and the energy is stored in the C1, and that time D2 is off. So it is a voltage. Why we call voltage doubler? Because the output is twice of the input. And Greneker is the two-stage voltage doubler. Here, the two-stage voltage doubler is used, and this is the voltage multiplier circuit. As the number of stages increases, the output voltage also increases. But we have to limit these stages because the reactance increases, and our conversion efficiency decreases. These are my PhD work, which I'm gonna discuss. First of all, I'm going to discuss my first work, a dual band rectifying antenna for RF energy harvesting. This is the antenna. This is the patch antenna with Sierpinski fractal shape on the ground plane, and it works for the dual band 2.1 gigahertz and 5.8 gigahertz. First of all, I designed this triangular slot antenna only that resonates at 2.1 gigahertz, and after introducing this triangular metal patch here, it provides me the suppression of suppression of higher order harmonics for 2.1 gigahertz, and further introduced 5.8 gigahertz with the help of this fractal shape. This is the second iteration. You can see here this is the reflection coefficient where I can achieve the two resonating frequencies, 2.1 gigahertz and at 5.8 gigahertz. And the second and third harmonics are removed with the help of that triangular slot, and able to achieve the high gain also. This is the rectifier of dual band network, and this is the open circuited stub used to match the network for 2.1 gigahertz, and this is LC network, that also called as L network, which are discussed in the matching network topology. Here, this is for the 5.8 gigahertz, and this diode is there for the rectification. C2 receives C2 stores the energy, and the output is received at the load resistance. This is the fabricated part of the rectifier, and this is the output voltage and conversion efficiency. As you can see, I was able to achieve 86% of conversion efficiency with the Schottky diode HSMS282E. Then I designed a triple band circularly polarized retina. This is the spiral slot antenna. First of all, I designed the monopole antenna that resonates at 2.4 gigahertz, and that resonates at 2.4 gigahertz. After this spiral slot introduced here, um, it resonates at 5.2 also, but and it also shows the orthogonal modes that shows CP also at 5.2 gigahertz. And this you can see the balun that is at the ground side. That the balun is used, that provides the perfect impedance matching, as well as shows the one more resonating frequency at 3.5 gigahertz. And to achieve the circular polarization at 2.4 and 5 at 2.4 and 3.5, we use this cross arm slot for 2.4 and this truncated corner for 3.5 gigahertz, and able to achieve circular polarization at all the three frequencies. This is the rectifier circuit. Three stubs are used to match all the three frequencies. First stub, the open circuited stub, that is used for the 2.4 gigahertz. Then two radial stubs are used here for 3.5 and 5.2 gigahertz, and able to achieve 85.6% efficiency with the RL load 500 ohm. And my third problem is a dual polarized multiband retina for RF energy harvesting. As I discussed before, if we need to, we're gonna harvest multiple bands or the broad band, so that more amount of power is received at the receiver, and more efficiency can be achieved. So I designed the six band retina basically, and it resonates at 4.75 gigahertz, 5.42 gigahertz, 5.76 gigahertz, 6.4 gigahertz, 6.9 gigahertz, and 7.61 gigahertz. And I'm able to cover the whole C band, that is 4 to 8 gigahertz. And circular polarization can be achieved at 5.42 and 6.9 and 7.61 gigahertz with the help of these circular slots and the truncated corners. This diagonal slit also provides me the circular polarization at 7.61 gigahertz. This is the fabricated structure of my antenna, the multiband antenna, and the result. these are the also very high, like 7.4 dBi is observed. The gain of around 7.4 dBi is observed.
Dr. Neeta Singh, we are not audible. Dr. Neeta Singh, are you there or some network problem? All the participants, please keep patience. There is some network issue on Dr. Neeta Singh's side. Please have a patience. She will come back shortly.
Hello? Hello?
Hello, yes, yes, now you are audible.
Sorry,
Yes.
sorry, sir, for the inconvenience. Sorry, sir, there is some
Okay,
glitches.
okay. Yes, yes, no problem. Carry on,
Sir,
please.
may I know at which slide I stopped?
Slide number.
I
Uh,
really don't know at
I
which
think
topic.
I think design two.
Okay, design.
Design third.
Okay, okay, sir. I pursued from that there only.
Okay, okay.
Sir, is it visible?
Not. No, it is not visible.
So now it is visible?
Not visible. No.
Not visible. Wait, sir. Sir, my side it is showing visible. It is presenting.
No, it is not visible. I think you should open the PPTs. PPTs are open. Your presentation is open.
Okay. PPT, my screen is visible, right?
Not. Your screen is not visible. Better you should leave and you connect again.
Yeah, yes, sir, I'll do that. Sorry, sir.
No problem.
So now it is visible?
It is visible. Dr. Neeta Singh, you conclude yourself within 6-7 minutes.
Oh, okay, sir. But
Okay.
my screen is visible, sir, or
Yes,
not?
yes. No. Screen is visible. You carry on.
Okay, sir.
Okay. But conclude in next 7-8 minutes.
Okay, sir. My third problem is dual polarized multi-band retina, and this is the six-band retina. This six-band antenna, 4.75 gigahertz, 5.42, 5.76, 6.4, 6.9, and 7.1 gigahertz. I was able to achieve 4 to 8 gigahertz. Like I cover whole C band, and this is the prototype of the antenna. In this, I was able to achieve the circular polarization at three frequencies: 5.42, 6.9, and 7.61 gigahertz. These are the slits through the slits and the circular slots, and with the help of truncated corners, I was able to achieve the circular polarization at all the three frequencies. And this is the fabricated prototype of the antenna. And this is the gain and the reflection coefficient. This is the rectifier, because to achieve as I already discussed, to achieve matching for multiband or the broadband is still a problem. So I use the three branch network. Each branch, that is each cell, each cell matches the network for the two resonating frequencies, and this again for the two resonating frequencies, and for this for the two resonating frequencies. And voltage doubler circuit is used here. And with the help of HSMS 2820, I was able to achieve 84% conversion efficiency. Then I have low profile multiband retina. Again, it is for the 6 band, but in the previous one, I only work for the C band, and in this paper, I work for the zero point 0.9, 1.8, and 2.4, 2.5 gigahertz, because more power, the more freely power is available at these frequencies. So I need to cover all these frequencies, and for this reason, I use fractal antenna, because fractal antenna provides the multiple bands and the broadband over the high frequencies. And this is the rectifier circuit. It is the same concept which is used in the previous one. The three branches are used here, and two resonating frequencies get matched for the each cell. And this is the adapter which is used to connect antenna and the rectifier. These are the output voltages of the all the six frequencies. And 78% conversion efficiency is achieved. The efficiency is less as the Schottky diode HSMS 2820, the conversion efficiency is less because it covers the large band, like three microwave frequency bands, L, S, and C. Hence, the conversion efficiency is little bit less as compared to the previous one, but the more number of frequency bands are covered. Then I move towards the millimeter wave frequencies. And this is the triangular shaped monopole antenna that is designed with these truncated corners. And I worked it, and I was able to achieve 5 gigahertz bandwidth with the help of this. And for this, to work for the millimeter wave, I go towards the graphene FET. Like graphene FET is the graphene FET provides the high stability and wider bandwidth as compared to the Schottky diode, because Schottky diode work at millimeter wave gives the narrow band, and this reason I moved towards the graphene rectifier, and I was able to achieve the conversion, high conversion efficiency even at the millimeter wave, that is 80%. And the quarter wave transformer is used here between the antenna and the rectifier. And the last problem is a compact graphene FET retina, which is which consists of SIW antenna. This SIW antenna provides fewer losses only on and avoid radiation leakage. And it is fabricated on RT duroid, and it provides me. This is as you can see, this is very dimension is very small, 3.2 cross 3.2 into 0.4, and it gives the 17 gigahertz bandwidth. The microchip photograph of integrated retina is there. You can see this, and this is the conversion efficiency and the output DC voltage. 80.32% conversion efficiency is achieved. Its size is very small, and with the high gain, that is 8.12 gigahertz. These are some applications which I need to discuss. What are the main applications? The smart city, smart vehicle, smart health, and smart house. In smart city, there are waste management is there. Authorities keep monitoring the bins. Smart energy is there. This system can manage the power system energy. Smart education is there in the smart city. Parents can keep track of their child as well, and the health monitoring system is also there. A smart system can monitor the health of each resident. For the smart vehicle, the electric vehicle can be charged even while moving with the help of IoT. We need not, the transmitting sources can be connected near the highways or the heavy traffic areas, and the e-vehicle fitted with the receiving antenna that receives the signal and charge by itself. And for the health monitoring system, in healthcare departments in future hospital and the medical healthcare centers may work on wireless electricity, so the implanted and implantable and wearable antennas are used that can monitor the patient's health, and it is very beneficial for the patients who are not able to visit to the doctors regularly, such as old patients, physically handicapped patients, and the wide tracity. Wide tracity, like MIT worked in 2006, but they demonstrated their experiment for the near field region only. But in future, maybe we get wide tracity for the far field also, like as we are getting wireless internet. This is the in we can use this for the disaster management system as well. In the situation of disaster, a medium is needed to maintain communication between the victims and their families. So the continuous power can be provided with the help of drones or the ships for the to the victims, and so that they can contact to their families or for the help. And wireless power supply to house from power station. The power transmitted from the grid is converted into EM waves and transmit to the transmitting antenna. An antenna is used between the pathways to receive the signal and transmit it to the receiving antenna that is connected at the rooftop of the house, so that wireless power is received at the house, and no need to use wires there. And at the conclusion, I concluded my talk as it is a very interesting topic. If someone wants to do research in the RF energy harvesting, it is very interesting topic, because now we are moving towards the wireless energy harvesting or the wireless power transmission system, and it can only be possible if we use the system like antenna or the rectifier that provides us the perfect matching and the high conversion efficiency with the high amount of power at the output. And various application we already seen that various applications are there for this RF energy harvesting system. So it is now, after some time in future, it becomes the very important part of our daily life. And also the batteries and the wires are not visible for us, as I already discussed. It is very harmful for our environment. And thanks to my guide, first of all, Vinod sir, that Kanojia sir, and then my Beg sir and Mainuddin sir for their valuable guidance. And through their guidance, I was only able to complete my PhD. And thank you.
Thank you, Dr. Neeta Singh, for a informative session delivery. Now quickly I am passing on 2-3 queries from the participant sides. The first query is,
Yes, sir.
how you simulate antenna and rectenna portion? Have you simulated separately or combinedly? That is the first query of the participant.
Yes, sir. I simulated it differently. Like I simulated antenna on HFSS, and I simulated rectifier on ADS, and then I integrate the both the like integrate the S parameters and the Z parameters in ADS for the impedance.
Okay, thank you. Now in design 3, what you have discussed today, dual polarization rectenna design. Antenna
Yes.
resonating at 6 band, including 3 different frequencies, what is the available power at 6.4 gigahertz, 6.9 gigahertz and 7.4 gigahertz frequencies?
So at these frequencies, the power is freely power is not available. As I already discussed, there are two types of sources. First one is the ambient source, and second one is the dedicated sources. For the dedicated sources, we can use these powers. Hence, I use the four design that is freely available, like at 2.4, 5.9, and 1.8 gigahertz.
Okay. Now, last query is, for matching circuit, how to represent the value of RLC to transmission line?
Sorry, sir. Can you repeat?
Yes. For matching circuit, how to represent the values of RLC component? Ultimately, that participant wants to know how to convert the lumped parameter into distributed parameter. Because everything RLC component you need to take on the distributed form in transmission line.
Yes, sir. We can easily convert on the basis of what are the impedance and what are the values of inductance and capacitance there, and on the basis of that we can convert it into the lumps. In the distributed circuits. As we already seen in that if we are talking about the transmission line, then we can convert the values of L, C. Like there are two ways to do it with the help of lumped circuits or with the help of transmission lines. So we can use in matching circuit the lumped circuit as well as the matching circuit as well as the tuning stubs also that will work on the distributive networks.
Okay, thank you very much. Now,
Sorry for the inconvenience, sir. Sorry for the
no, that was not because of you. It is applicable to all. It can happen to any node, no problem. Anyway, thank you very much.
Thank
First
you.
of all, for accepting the invitation, and then
So that's my honor.
second, thanks for a wonderful delivery of the session. And now you can stop sharing your screen so that
Yes.
we can start the process for second speaker. Okay. Anyway, okay. Now I think it is coming. Yes. Okay. As a second speaker of first day of SRC 2020, Mr. Sam Gosim from İzmir Kelebi University, Turkey is there. Sam Gosim received his BE degree in Electrical and Electronics Engineering from Ankara University, Turkey in 2016 and his MSc degree in Electrical and Electronics Engineering from İzmir Kelebi University, Turkey in 2019. Presently, he is working as a PhD scholar in the Department of Electrical and Electronics Engineering at the same university, where he has been working on electromagnetic fields and microwave techniques, especially in the area of RF energy harvesting system. With this, I welcome you, Mr. Sam Gosim, and invite you to start the session.
Okay, thank you for your okay, my screen or my voice is okay. I'm going to present our presentation.
Yeah.
Hello to everyone. Good and healthy days from everyone from Turkey, and good evening or good afternoon for everyone. I'm Cem Göçen. First of all, thank you very much for your kind invitation for this event. I completed my master's degree in 2019 by working on RF energy harvesting systems. In this special section, I will talk about the publications we made with my advisor, Dr. Mir Palandöken, and my thesis. My presentation title is Different Radio Frequency Energy Harvesting System Designs. These are my presentation outline. I'm going to present my study in three main titles. First one is the introduction, second one is the design considerations, numerical and experimental results, and the last one is the conclusion part. Also, I'm going to start with the first part. In this part, I will describe RF energy harvesting systems. I will talk about this system, also RF energy harvesting system objectives and motivation, and then I will present some literature review on energy harvesting systems. In RF energy harvesting system, there's also a energy harvesting technique has gained a lot of attention from both academia and industry due to its promising features for green communication networks, wireless sensor nodes, and also Internet of Things technologies. The RF energy harvesting is based on the gathering of RF signals in the RF fields generated by electromagnetic waves radiated by source such as TV towers, wireless radio networks, or cell phone towers. These RF signals are captured and converted into functional DC voltage by using a rectifying circuit directly connected to receiving antenna. The amount of the harvesting power depends on the average power density of the location, efficiency of power conversion, this means RF to DC conversion efficiency, and physical size of the energy harvesting system. Also, the performance of the system depends on the efficiency of the rectanna, which can be improved by the antenna design, impedance matching circuits, and modeling of diode. Diode means using an RF to DC rectifying circuit. In this system, the operating frequency of an antenna varies in wide range depending on many factors such as local regulations, target applications, and the transmission protocols. It's important to note that increasing the operating frequency results in a higher power consumption and more complicated design. First of all, I'm going to talk about RF signal. Electromagnetic waves are freely available in increasing frequency and power level in the environment, especially in densely populated urban areas. The ambient RF sources can be divided into two types, static and dynamic ambient RF sources. Static ambient RF sources are the sources which transmit RF signals constantly. This means, for example, TV towers and FM base stations. The transmit powers of these RF sources are usually high, up to 1 megawatt for TV towers. The transmitter to RF source distance can vary from several hundred meters to several kilometers. Next one is the dynamic ambient RF sources are the sources which operate periodically or randomly with typically lower transmit power, for example, Wi-Fi modems. The transmitter to RF source distance is often very short, between 1 and 20 meters also. Radio error energy harvesting system, first element is an antenna in receiving mode, receiving antenna. An antenna is an essential component used to receive ambient electromagnetic signals from the radiating sources. Thus, the design of the antenna can significantly affect the performance of the RF energy harvesting system. The antenna design required the best choice of the substrate, the electric constant, length, and width of antenna. This means physical dimensions of antenna, and the ground plane, and also top layer structure designs. Receiving antennas are generally preferred in microstrip type due to their low profile, physical properties, and low fabrication costs. There is a important antenna parameter is antenna gain. Antenna gain is the amount of power transmitted in the direction of peak radiation and to an isotropic source. In general, the higher antenna gain leads to the longer range of transmission. Thus, it's important to calculate the antenna gain based on the target communication distance when designing the antenna. Next element of this system is matching network. In the RF energy harvesting system, an impedance matching circuit steps up to power transfer from the antenna to the rectifying circuit, and rectifying circuit rectifies the gathering RF signals, which is from receiving antenna part, to output DC voltages. Also, the input impedance of receiving antenna is 50 ohm because it's general determinant compatible with the line impedance. Also, the input impedance of the RF to DC rectifier circuit has a reactive value due to diodes and capacitors used in voltage multiplier circuits. In addition, the circuit itself exhibits nonlinearity due to nonlinear characteristic of using diodes in rectifying circuits. For this reason, the impedance mismatch between the antenna and the rectifying circuit is prevalent. Impedance matching circuit is vital in optimizing the performance of the RF energy harvesting system. Next element of this system is RF to DC rectifying circuits. And RF to DC rectifying circuit converts the captured RF signals in AC alternating current form type from the receiving antenna and provides a DC output voltage to the DC load. A significant challenge of the rectifying circuit design is to generate DC voltage from little input RF power. The major design parameter that directly affects the output voltage of the ambient RF energy harvesting circuit is the number of rectifier multiplier stages. Also in the figure, there is an N stage multiplier in here. We see that the efficiency is not simply higher at the desired input power as the number of stages increases. The increment on number of stages also causes shift on the peak of efficiency curve tower height powers. Rectifier technologies are examined in two main categories as diode-based and transistor-based rectifier circuits. Diode is using these systems in generally. The diode is the main component of the rectifying circuits. Therefore, the diode chosen for RF energy harvesting circuit should have a least possible turn-on threshold voltage. Furthermore, these diodes must have faster switching time compared to a traditional diodes, since RF energy harvesting occurs at high frequencies. For these reasons, we selected Schottky diodes for our ambient RF energy harvesting circuit designs. Schottky diodes contain a fast metal semiconductor junction with a forward voltage drop of less than 0.15 volts compared to semiconductor traditional diode junctions. Last part of this RF energy harvesting system is load part, the DC load part at the end of the energy harvesting circuit generally consists of devices with low power consumption. The load impedance should be selected carefully because it's directly related to impedance matching with the antenna and has bearing on maximum energy transfer. The electric current consumption of a low power device also recommended in right figure changed its operation, such as active sleep and deep sleep states. This means that the impedance of the sensor is changing with status of its state. This motivation behind of this study, the energy nature can be converted between different forms, stored, transferred, and never eliminated. With the developing technology, there has been a significant increase in energy resource resource diversity, energy storage capacity, and the conversion efficiency of energy between types. Energy supply has always been a critical limiting factor to the lifetime of some electronic devices, especially wireless devices. Despite the advantages of the limited battery life and where there is difficulty in energizing, by exploring possible alternatives to conventional disposable batteries in powering the electronic devices with low power consumption, thus making these devices indefinitely self-sustaining devices. One possible solution is to use radio frequency energy harvesting, in which ambient energy is gathered, converted into electrical energy, and use these type devices. Objectives are here. The key challenge in designing an ambient RF energy harvesting circuit is the need to operate with low power RF signals. The average power amplitude of ambient RF signals can be as low as minus 25 dBm, which means that the amplitude of the received signal power is less than approximately 3 microwatts. This generates also 4 milliwatt RMS and approximately 6 milliwatt peak AC voltage for typical 50 ohm antenna. An efficient antenna for maximizing the reception of the ambient RF signals, a matching network to match the antenna impedance with the complex load impedance, composed to inductive and capacitive element in order to achieve maximum power delivery from antenna to the RF to DC rectifying circuits. Optimization of the rectifier circuit for RF to DC conversion efficiency. There is a literature review. RF energy harvesting systems are often used for two different purposes in the literature. First one is to meet the energy needs of low power devices. Second one is the storage of harvested energy in storage unit. RF energy harvesting system is able to design for operate in the 0.3 to 300 gigahertz in operating bands. Generally, the operating bands of system are selected according to RF source in operational environment or from the common bands of use. Also, generally using at zero bias Schottky diodes used in RF to DC rectifying circuits. Also, to sum up the literature review, different antenna and circuit design used. There is a different the electric resonator antenna, microstrip antennas are used. Also, average system output is 1.5 volts for minus 15 dBm to minus 10 dBm input power values. Average RF to DC system conversion efficiency is 60%. There is many RF energy harvesting system are investigated in literature. System performance table is created for 900 megahertz also and 2.4 gigahertz. There is a sixth example from literature. The second part, this part consists of three different RF energy harvesting systems. Two of them are designed operated in the 900 megahertz band. This means in Turkey GSM band, and the other is designed to operate in 2.4 gigahertz. This means in Turkey ISM band. In Rectenna design one, this is operating at 900 megahertz, and this design consists of split ring resonator antenna, single stage Willard voltage rectifier, and as a DC load KY 0 to 8 digital temperature sensor as a DC load. In the antenna design, split ring resonator type designed and split ring resonator antenna designed and numerically calculated in CST Studio design program. In antenna design, also this Also, this design fabricated with Roger substrate. In antenna design, split ring resonator structure on the top layer. Also, in the ground plane, framed elliptical structure are from the CST results and simulated reflection coefficient result at the resonance frequency 900 MHz with the return loss 21 dB with 10 dB bandwidth of approximately 35 MHz is obtained in measured reflection coefficient result at the resonance frequency 890 MHz with the return loss 21 dB with 10 dB bandwidth of 51.3 MHz is obtained. Parametric study in figure 4 is performed for the adjustment of resonance frequency and 10 dB bandwidth of energy harvesting antenna. In this study, only one parameter is changed. Only one parameter is changed. The others are constant. Also, RG1 parameter on the ground plane is effect on the 10 dB bandwidth and also resonance frequency, and also the RG2 parameter is effect on the return loss value at the resonance frequency. RG2 parameter is on the again ground plane. Antenna surface current distribution in figure 5 shows the operational principle of antenna. The operational principle of antenna is in the form of the lambda resonance characteristic of split ring resonator capacitively coupling on the top layer of the antenna, and in the form of the electrical coupling between the framed ground of the antenna. Also, figure 6 shows the polar radiation pattern of this antenna design, X, Y, YZ, and XZ planes, respectively. The half power beamwidth is approximately 95 degree on antenna azimuth plane. Azimuth plane means in this design XY plane. For an investigation, antenna gathering performance, antenna port is in the CST program. Antenna port is distracted and lumped element is 50 ohm resistant, is mounted at the antenna port point. The radiating field is modeled as the radiating field means that RF source in freely available in environment. Is modeled as the plane wave excitation experimental setup shown in figure 7, and in a far-field region with a distance of 500 millimeters from the antenna. Figure 8 shows the current and voltage values on the lumped element. The voltage value is obtained 88 millivolts, and the current is obtained 1.7 milliampere, and the power and the obtained power is approximately minus 11 dBm. In the first rectangular design, impedance matching and RF to DC rectifying circuit are in figure 9. Impedance matching and RF to DC rectifying circuit is designed and numerically calculated in ANSOF designer program. With this single stage rectifier topology is used based on also zero bias Schottky diode, detector diode, SMS 7630 Skyworks, in conjunction with lambda over 4 impedance transformer with an inductor as a matching circuit element. As a DC load are in figure also. The simulated reflection, figure 10 shows the input reflection coefficient of the circuits at the different input RF power levels. The simulated reflection coefficient is obtained minus 30 dB at minus 30 dBm RF input power. Figure 11 shows the DC output voltage of RF energy harvesting system. Figure 12 shows the RF to DC conversion efficiency at different RF input power values. And the last one is the DC output voltage at different RF input power values. The simulated RF to DC conversion efficiency is obtained 75% at minus 11 dBm input power with 1.7 DC output voltage. This is also a summary table for Rectena design one. Antenna performance, also the system performance parameters are here in table, which I have just presented. Rectena design 2 this design is operating at also same 900 megahertz, and this design consists of Hilbert fractal resonator antenna, also again single stage. There is a different voltage rectifier, and also there is the same DC load KY 0 to 8 digital temperature. In the antenna design, this antenna design is designed and numerically calculated in CST Studio Suite. Also using this, you also fabricated with using a Roger substrate. In antenna design, Hilbert fractal resonator structure on the antenna top layer. In the ground plane, remote patch structure with asymmetric feed line on the ground plane. In the simulated reflection coefficient result at the resonance frequency 900 megahertz with the return loss 34 dB with 10 dB bandwidth of 40 megahertz is obtained. In measured reflection coefficient result at the resonance frequency 890 megahertz with the return loss 32 dB with 10 dB bandwidth of 55 megahertz is obtained. Also, antenna surface current distribution in figure 16 shows the operational principle of antenna. The inner part of the one branch of symmetrical resonator is a second iteration Hilbert fractal curve, whereas the outer one has the shape of the first iteration Hilbert fractal curve to decrease the resonator form factor. The main aim is therefore to introduce a novel antenna topology consisting of various combinations of different orders fractal curve iterations. Also, figure 17 shows the polar radiation patterns of this antenna design from CST Studio Suite. X, Y, YZ, and XZ planes respectively. In figures, the half power beam width is approximately 100 degree on the antenna azimuth plane. Azimuth means XZ plane in this antenna design. Also, for an investigation, again, antenna gathering performance, antenna port is distracted and lumped element is mounted at the same point. The radiating field is modeled as the plane wave excitation. The plane wave excitation power is 1 volts, electric field 1 volts over meter. Also, the experimental shown in figure 18 in a far field region with a distance of 500 millimeter from the antenna. Also, figure 19 shows the current and voltage values on the lumped element. As the obtained voltage is 42 milliwatts. Also, obtained current is 0.82 milliampere. Also, the obtained input power is equal to minus 14.7 dBm. Impedance matching and RF to DC rectifying circuits with R load DC load part. This design is designed and numerically calculated, and again ENSOF designer program with the single stage voltage rectifier topology based on zero bias Schottky detector diodes SMS 7630 Skyworks. As a matching circuit element is only one inductor in conjunction with inductor. Also, simulated results are here in this for this circuit design. Figure 21 shows the input reflection coefficient of the circuits at different RF power levels. The simulated reflection coefficient is obtained minus 28 dB at minus 27 dBm RF input power. Figure 22 shows the DC output voltage of the RF energy harvesting system. Figure 23 shows the RF to DC conversion efficiency at different RF input power values. And the last figure is the DC output voltage levels at different RF input power values. The simulated RF to DC conversion efficiency obtained in the maximum point 70% at minus 11 dBm input power with 1.87 DC output voltage. Also in the input power is equal to minus 5 dB. DC output voltage is obtained 2.8 volts, shown in last figure 24. Also summary table here is about rectangle design, two antenna parameters, also RF to DC design, circuit design parameters are here. Next design, third rectangle design 3. Third one is operating at 2.4 GHz, and this design consists of a T-shaped resonator antenna and single stage voltage rectifier and optimized DC loads. There is a no DC load port for the investigation DC load. T-shaped resonator antenna is designed and numerically calculated in, again, CST Studio program. In antenna design is also using fabricated with Roger substrates. In antenna design, T-shaped resonator structure with U-shaped feeding line on the top layer. The upper and lower rectangle structures with a connection paths on the ground plane. Performance parameters of the antenna in simulated reflection coefficient result at the resonance frequency 2.38 GHz with the return loss 27 dB with 10 dB bandwidth of approximately 1 GHz is obtained. In measured reflection coefficient result at the resonance frequency 2.44 GHz with the return loss 34 dB with 10 dB bandwidth of 240 MHz is obtained. There is some difference between measured and simulation results. This difference due to fabrication process. There is in the figure connection paths with in the here G4 parameter are here in the figure is not similar to design simulated and designed prototypes for in fabrication process. Parametric study in figure 27 performed for the adjustment of the resonance frequency and 10 dB bandwidth. In parametric study, only one parameter is changed, others are constant. There is a two parameters. First one is the G. There is a wrong with in figure. First one is the G4. This G4 is the connection path parameter. This effect on the resonance frequency and 10 dB bandwidth. Also, the second parameter is C2. C2 is effect on the a little bit 10 dB bandwidth. Also, effect on the resonance frequency. T-shaped resonator antenna surface current distribution in figure shows the operational principle of antenna. The antenna operation principle relies on the resonant excitation of mainly capacitively coupled directly fed fork shaped resonator to parasitic T-shaped resonator. In the in conjunction with the rectangular slot resonator in the ground plane. Figure 29 shows the polar radiation patterns of X, Y, YZ, and XZ planes, respectively. The half power beamwidth is obtained 81 degree on antenna elevation plane. Elevation plane means YZ plane in the antenna design. Also, antenna input performance, input power measurement setup is modeled CST again. The ambient radiating field is modeled as the plane wave excitation, 1 volt over meter experimental setup in a far field region with a distance 40 millimeter from the antenna. In the lumped element, voltage is obtained 63 millivolts and current is obtained 1.3 milliamperes. This obtained power is approximately minus 11 dBm again. The impedance matching and RF to DC rectifying circuit is designed and numerically calculated in ANSYS electronic desktop program with a single stage voltage rectifier topology based on zero bias Schottky detector diode SMS Skyworks. Again, matching circuit is only inductor element in figure. Also, R-load designing. R-load is here achieved optimized R-load resistance value is 11 kilo ohms. In the results of this simulation, the simulated figure also 33 shows the input reflection coefficient of the antenna at different input RF power levels. The simulated reflection coefficient is obtained minus 27 dB at minus 11 dBm RF input power. Figure 34 shows the DC output voltage of the RF energy harvesting system. There is a not matching signal in black one in here. After matching, there is a AC form of the signal. Also, output of the this RF to DC rectifying signal is blue one in here. Figure 45 shows the RF to DC conversion efficiency at different RF input power values. There's two values are here. One of them is the 49%, and the second of is 80% are here. And the last one is the DC output voltage levels at different RF input power values in figure. The simulated RF to DC conversion efficiency is obtained 49% at minus 11 dBm input power with 0.75 DC output voltage. Also, the simulated RF to DC conversion efficiency is obtained 80% at minus 6 dBm with input power is with 1.75 DC output voltage. There is a summary table for rectangle design tree. Antenna parameters, also RF to DC rectifying circuit design parameters are design performance parameters are here in the table. There is a last. Sorry, there is a problem in. This is a conclusion part. In this part, I will talk about the conclusion remarks and future work. Designing RF energy harvesting system requires three main steps. Firstly, power requirements of the RF energy harvesting system must be defined. It's common for autonomous systems, the power consumption of their circuits to rise on if necessary. Therefore, it's common for the autonomous system the power consumption of their circuits to rise only if necessary. Therefore, the time between active cycles and the average power consumed must be considered. Secondly, a suitable RF energy source must be selected based on requirements. Dedicated RF transmission may be used for applications where no ambient RF signals is available or a RF signal is available, but its power density is not sufficient for the application. Factors such as frequency of the RF source signal, physical location of the device means low power consumption as a DC load in the RF energy harvesting system, or size limitations. Size limitations is design parameters of RF to DC RF energy harvesting system should be considered in that stage of the planning. In the last stage, an efficient RF to DC conversion circuit must be selected and implemented for an efficient power conversion of the incident RF power energy to DC energy suitable for the load. In this presentation, 3 energy harvesting systems are designed, built, and tested for ambient RF power existing in GSM and ISM bands. More power harvested for low input RF power levels, less physical size, increased reliability, and improved converter power efficiency are accomplished compared to conventional RF energy harvesting systems. In the design one, 1.7 output DC voltage with 75% RF to DC conversion efficiency at the center frequency of 900 MHz for minus 11 dBm input power is obtained. In the Rectifier design to 1.87 volts output DC voltage with 70% RF to DC conversion efficiency at the center frequency 900 MHz for minus 10 dBm input power is obtained. In the Rectifier design 3, 0.75 volts output DC voltage with 49% RF to DC conversion efficiency at the center frequency of 2.4 GHz for minus 11 dBm input power is obtained. And the discussion part of this presentation, one of the greatest challenges for wireless devices soon is their sustainability. As the number of wireless devices rises, handling their energy supply becomes a complicated task because traditional batteries charging or swapping inconvenient due to their large quantities. The solution to this problem by providing RF energy to every device simultaneously that is harvested through a rectangle and converted to DC electricity. The focus in our study is simulate the performance of an antenna and rectifier to maximize the efficiency at low input powers. The rectifier and antenna should be manufactured and tested to verify the simulation results. Also, the output DC voltage value level and RF to DC conversion efficiency can be improved in using these 3 steps, increasing the total number of the antennas, using an antenna array, increased by using multi-stage voltage rectifier circuit. There is a problem with there is a complicated problem in design procedure, increased by improving the design of the multi-band RF energy harvesting system. In the future work of these RF energy harvesting systems, a big part of the modern circuit, a big part of the modern printed circuit board PCB layouts is the power supply network, which may include thousands of nodes, tracks, vias, and etc. Implementing RF energy harvesting approach to the individual components design may contribute to the improvement of the integration factor. Using a dedicated RF radio frequency source located in the device compartment may power hundreds of electronic components at the same time. Moreover, using different frequencies as a RF energy sources for distinguished modules would let us optimize better control the resources. More research should also be put into designing rectifier able to harvest power in multiple bands. This is especially interesting since the efficiency of rectifiers is low at low input powers. A multi-band system should therefore be able to both capture more power and rectify this power in a more efficient manner. More techniques for optimizing the rectification process should be investigated. Power conversion efficiency values in the range of approximately 50% are proved to be lowest efficiency achieved in RF energy harvesting system compared to efficiencies of the other components. There is a new method for maximum power point tracking technique, which is already popular in solar energy harvesting. The research study introduced in this distortion has the potential many exciting applications such as smart sensor applications, implemented biomedical devices, also using compatible with body devices, and ultra low power applications by providing solutions in places where energy sources are limited. Further research of energy harvesting circuits could be towards flexible printed circuit boards, where power management circuitry and smart sensors could be integrated on or under the energy harvesting source. Okay, my presentation is over. Any question?
Thank you, Mr. Gosen.
Thanks for your attention.
There is one query on your talk. One participant is asking that how to build a plane wave in CST to simulate your design.
Okay, I didn't hear properly.
How to build plane wave in CST software?
Okay, I didn't hear properly.
Okay, can you go to chat box? Can you please go to chat box?
Okay, I'm.
Okay, there is one query at 9:05 p.m.
9:05 p.m.
Okay, there is only one query. You directly read that one and.
Okay, I didn't see. Okay. Okay, I see. There is a CST in plane wave excitation. There is no using its different ports. There is a in the CST Studio program. There is a plane wave excitation button in below in the simulation program. We use this using plane wave simulation, and then click simulate this program. We obtained at the lumped element voltage and impedances. Which boundary conditions we use in the compatible with far field dimensions. We design using a vacuum substrates for design a boundary conditions.
Okay. I think no further queries there from the participants. Anyway, thank you, Mr. Gosen, first for giving the consent for delivering the talk on this emerging area of RF energy harvesting system, especially what you are doing there in your university. With this, I must say thank you and bye-bye too. And finally, please convey my regards to your supervisor, Professor Plandoken.
Okay, thank you.
Thank you. You can stop the sharing. Now, finally, the end of the today's session is now about 2 hours. That is, these two lectures have been successfully delivered. In first lecture, there was some glitches due to some internet interruption. Anyway, both the sessions were quite good and informative. Hope all the participants have enjoyed them. keep this type of interest for the remaining 4 days, and definitely tomorrow onward you will get some different flavors in the ongoing sessions. Thank you once again. Bye. Good night, good afternoon, and good morning to all of you.